an engineering problem where the reference signal is sinusoidal. And I haven't, so I haven't finished this discussion. If anyone, if there is a majority of people here, only if there is a majority who want to understand how precisely I got from here to here, I can do it. Because that's not the topic of this mini course. But if you want, I can. So, is there a majority of people who want to see that? Okay. So, the switches act in such a way that after the switches work very fast. As I said, several tens of kilohertz, and then you average the signal that you obtain between these 2 points. Because it's a very high frequency switching signal, you average it, and this average signal is this G. Oh, why did I write U here? I'm sorry, that should. Oh, you know what? Let's call it U. Let's call it U. Yeah, let's call it U. It fits better with the pictures that we had earlier. Let's call it U. So the averaged voltage between these 2 points, we call it U. So I delete G, and this is U. Okay, and this voltage is now applied to the inductor, and through the inductor it goes to the grid. You understand that there must be an inductor here. If you are an engineer, you understand, because I cannot connect a voltage source to another voltage source. You cannot connect together two voltage sources, because then any difference between the voltages will create an infinite current. So there must be something to separate the two voltages, and people put an inductor, because the inductor not only separates the voltages, but it does not consume energy. An inductor is a purely reactive element, meaning that on average the power that it consumes is zero. And so we need such an inductor to separate the two sides. And this inductor, when you make a real inductor, then this inductor will also have a resistance. So we have to represent the inductor as being a resistor in series with an ideal inductor. Ideal inductor is of course represented by, let's call the voltage across it by V. So the current I, so V is equal to L times I dot. I dot meaning the derivative of the current. So this is the equation of the inductor, and I want now to see what is actually my system. So my system now is that I have this voltage between this point and this point. It is U minus Vg. Yes, here I have the voltage U with respect to ground. I consider this to be the voltage 0. Yeah. So this is the voltage U with respect to ground, and this is the voltage Vg with respect to ground. So on this inductor, in total, I have the voltage U minus Vg. So okay, let me write it here. The total voltage U minus Vg is equal to the voltage on the resistor, which is R times I, plus the voltage on the inductor, which is, as I wrote here, is L times I dot. L times I dot. Yes, and now that means that I have the following system. If I do Laplace transform here, so U hat of S minus Vg hat of S is equal to R plus Ls. You see the S comes from the derivative here, multiplied with I hat of S, which means that I hat is 1 divided by R plus Ls times this difference, U hat minus Vg hat of S. Yes, so if I represent my system, then I have the Planck transfer function 1 divided by R plus Ls, and in goes this difference. So I have U and Vg. This comes with a minus sign and this with a plus. And here comes the current I. Yes? So you understand that my plant looks like this. Yes? Is that understandable? Sorry that I'm a bit improvising here because it was the example that you proposed, right? Okay. So now here we have a reference signal. I told you earlier, meanwhile I deleted, that we want I to be proportional to the voltage Vg. So we have a reference voltage, we compare I to the reference voltage, which is proportional to Vg, so minus plus to compare them. And now this is a tracking error, E. And now we want a controller here. We want a controller so that this tracking error should ideally tend to 0. Right? So this is now the diagram. It's actually, after you write it like this, then it's sort of a very simple problem formulation. You have a plant which is a transfer function of order 1. Yes, stable, obviously stable. And you want to follow a reference signal which is sinusoidal with frequency equal to the frequency of the grid. And you have the disturbance signal, so you notice that D is equal to minus Vg, yes, because you have here this minus sign. So that means that the disturbance, if I would change here to plus and would write D, then the disturbance would be equal to minus Vg, right? So if I want to make it like the previous picture, yeah, then it means that this is my disturbance, minus Vg. So the grid voltage is my disturbance, and okay, minus the grid voltage is my disturbance, and I want to track a sinusoidal current reference which is in fact proportional to the grid voltage. So what do we have? The disturbance is sinusoidal and the reference is also sinusoidal. Yes? So we are exactly in the situation that was here but it disappeared meanwhile, but you know what I mean. How can you solve this? Let me bring it back up. I don't know why it disappeared. Yeah. Okay. So you see, this plant, it's a constant divided by 1 plus Ts. It's exactly, I mean, I can write this. I can write it exactly like this, right? If I want. You just divide it by R. So this constant K will be 1 over R, and this constant T will be equal to L divided by R, right? So it's exactly this situation, and I need to eliminate grid frequency both in the disturbance and in the reference, and so I can use this controller, and you can check that this controller indeed does a job, which means we have to check that the closed loop system formed by this and this is stable. It's a little exercise. Here is another exercise for you. No matter what the constants are, so as long as these are positive constants, K and capital T are positive constants, omega 0 is another positive constant, capital K is another constant, positive constant. When you connect them together, it will be stable. It's an easy exercise based on the proposition which we did, that you have to compute the sensitivity, check that the sensitivity is stable, and that there are no unstable pole zero cancellations. When you look, it is obvious that there are no unstable pole zero cancellations, so that's okay. So you only have to check that the sensitivity is stable, and that's very easy to check. So we can, so this is a problem which is faced in every rooftop PV power generator. They want to control the current. Now there is a little discussion here which I have not gone into, namely how to determine this reference signal R. You could say, but it wouldn't work, you could say that okay, it is a constant times the grid voltage, but that is not correct to do it that way. It's actually more complicated than that. For several reasons it's more complicated than that. First of all, because you don't know what this constant should be, because the power that you generate is this current I times the grid voltage. Yes, that's clear. And if these indeed are sinusoidal signals, then the average power, I use now this bar to denote average, is equal to the RMS value of the current. Do you know what RMS stands for? Root means square. It means you average the square of I and take the square root of it. Yes? Sometimes they call it the effective value. So this is the RMS value of the current times the RMS value of the grid voltage, RMS, times the cosine of the phase difference between this sinusoidal signal and this sinusoidal signal. Now, in our case, we choose this phase difference to be 0, so the cosine of 0 is 1, so you can forget about this. Yeah, if we managed indeed to make the phase difference between them to be 0, then this is 1. Yeah, everybody sees what I'm talking about. Okay. Okay, so this power has to be this, but on the other hand, the power that I can extract from the solar panel on my roof depends on how strong the sun shines. So that depends on the hour of the day, and it depends on whether there are clouds or not. So that is something which changes. So I cannot fix a constant and say R is a fixed constant times Vg. That is not possible. I have to adjust it according to the intensity of the sunshine, because I have to achieve that this product should be exactly equal to what the solar panels can give. And actually it's even more complicated than that, because I do not know exactly how much the solar panels can give. I have to find the maximum point of the solar panels. I have to adjust the voltage here, this voltage on the solar panel. I have to control it so that it reaches the voltage at which the power is maximum. The power delivered by the solar panel is maximum. So that means that there is actually another feedback loop around this system which searches for the optimal voltage, and it adjusts the power by adjusting the constant. So R is some constant K times Vg, yes? But this constant is not a constant really. It's not really a constant. It is given by another feedback loop built around this system, which adjusts K so that at the optimal value I get the highest possible power. This is not our issue to discuss this in depth. There are many algorithms which are called maximum power point tracking algorithms, MPPT, which search for the optimal value of this constant so that the voltage will stabilize at the optimal voltage so that I can extract the most power from my solar panel. But this is outside the scope of this course. Now, I want to say another thing. This choice that it is K times the grid voltage is also not exactly the truth. I'm always hiding the ugly details. In reality, it's more ugly than that, because the grid voltage is not exactly sinusoidal. if you look at the grid voltage, it's actually quite dirty. It has, it's not a sinusoidal wave. It is distorted. And it is distorted because of various consumers who do not act like resistors or like inductors or like capacitors. They act in a nonlinear way. And if you have a nonlinear consumer, then the current that they consume will not be a sinusoidal current. And if the current is not sinusoidal, then the voltage that the utility company gives us gets distorted. A current which is sinusoidal, even if it is out of phase with the voltage, and it's usually out of phase, will not distort the voltage. But a current which is not sinusoidal will distort the voltage, and that's why the utility companies have regulations that consumers are not allowed to be too nonlinear. So what does it mean too nonlinear? There is a measure for that. It's called the total harmonic distortion. You do the Fourier expansion of the current of a consumer. So it's a Fourier series of the current. Then you have a fundamental component, which is a component at the grid frequency, 50 Hertz. Yes? And then you have many more components, which are the distortion. And you compute the sum of the absolute value squared of all the components which are not the fundamental, divided by the sum of all the components squared. So in other words, L2 norm over one period. The L2 norm over one period is the same as the sum of all the Fourier coefficients squared. You know that, yeah? Now, so you take the sum of all the Fourier coefficients which are not the fundamental, divided by the sum of all the Fourier coefficients squared. Yes? So on top you leave one out, the fundamental. On the bottom you leave all of them. And this ratio is called the total harmonic distortion. So ideally it should be 0, because there should not be any components other than the fundamental component. But there are, and so you get, this ratio is expressed in percentage, and it should be something like 2-3%. It depends if each country has its own regulations, how much is allowed. So in general, you try to be to take a current which is close to sinusoidal. Okay, but nevertheless the grid is distorted. It is not exactly sinusoidal. And now the challenge is the following. You look at the grid voltage and it's not sinusoidal. But you want nevertheless to create a reference voltage R which is sinusoidal, and it should be proportional to the fundamental component of the grid. So when you take the Fourier expansion of the grid voltage, you look only at the fundamental component, which of course is sinusoidal, and you want your current reference to be proportional to the fundamental component of the grid voltage. Now, how do you extract the fundamental component of a periodic but not sinusoidal voltage? So how do you build a device which receives as input a non-sinusoidal periodic input, and possibly also other noise, possibly also other frequencies which are even not related to your grid voltage, and at the output of the device you should get a sine wave which is proportional to the fundamental component of the voltage of the input signal. Now such a device is called a phase-locked loop. Yes, I mentioned earlier today a phase-locked loop. So a phase-locked loop, first of all, from a mixture of several approximately sinusoidal signals, it extracts only one, and you can hop from one to the other. You can choose which one you extract, but in the case of the grid, it's clear which one you extract. So you extract one of them, and then from this one, you extract only the fundamental component in the Fourier series. Yes, that is the role of a phase-locked loop. So in order to obtain this R signal here, this R signal actually comes from a phase lock loop, and it is multiplied with this constant k, which is not a constant, I told you, this k, and here is a phase lock loop, PLL, and this receives as input the grid voltage. So the grid voltage enters the PLL, that the output is only the fundamental component, it gets multiplied with this k. This k is controlled by what is called the MPPT algorithm, the maximum power point tracking. And then it gets to be our reference signal. So the picture is actually more complicated, and I did not show you what this is and what this is. Yeah. So but it is an example of a system with sinusoidal reference signal and sinusoidal disturbance signal. Now, any other idea of a system with a sinusoidal reference or disturbance signal? Can anyone else think of something? From whatever you did in... What? A flexible mode. So explain more.
I mean, well, maybe you could try to attenuate the disturbance of a flexible mode, which is, for example, another review.
So give a more precise description of the problem.
You have robot that has a flexible appendage.
Yes.
And you want to be precise, but you know that if you are acting on, well, but this is not exactly making a reference.
Okay, so you have a robot, yeah. And you want the robot to do some movement, okay? And now you want to have a sinusoidal reference or disturbance signal. So
in flexible mode will be a disturbance. And then
wait, you have to be careful now. The flexible mode, you mean the flexible joint of the robot?
Yeah,
they vibrate. Yeah. Okay, now that's not a good example, because then it means that this vibration is internally generated. It is part of the dynamics of the system, and when you act on the system, the frequency of it will change, or hopefully it will disappear completely, right? So it is an internal maybe not instability, but maybe close to instability, because probably it's damped oscillations, right? So it is a mode which is close to instability, meaning close to the imaginary axis, but it is part of your system, it is part of the plant. It is not coming from the outside, but you can take the same robot arm and you can say that there is, you are in a vibrating environment. There is a motor next to your robot and it shakes, and you want to eliminate the effect of this shaking of the environment. So the shaking comes from the outside, yes? It's a disturbance which acts on your flexible robot, and you want to and you know it's very important to say you know the frequency of the disturbance. And if you know the frequency of the disturbance, then you want to eliminate its effects, meaning that you want to create a controller with an internal model, hopefully, that, so I mean a controller with poles at the relevant frequency, so that the effect of the disturbance, which comes at a known frequency, is eliminated. Okay, let me mention a closely related situation. Let's say that you have a motor rotating, and or not a motor, but some big machinery is rotating, and the mechanical load of this machinery changes with the angle. So let's say that something is rotating, and each time, let's say it has some protruding part, and each time it comes to a certain part, it has a friction, and then the torque is big, and then it moves away from this contact, and then the torque is small, and then it comes back, and again it moves, it touches here, and the torque is big, and then it moves away, and the torque is small. This is actually very typical in drilling. If you have, if you drill a hole, for example, you drill a tunnel, then you have a rotating drill, and depending on the structure of the stones where you are drilling, at certain angles you have big resistance because you have to cut some hard stone, and at other angles the resistance is smaller. So you have a certain periodic pattern for the load torque of this drill. And you can invent also many other examples where you have a periodically changing torque acting on a rotating machine. It can also be internally generated by the motor itself. Many motors have internally a mechanism by which the torque changes depending on the angle. Never mind why. Okay, so and let's say that in such a situation you want to control that the angular velocity of your drill should be constant. Then you are tracking the angular velocity of your drill, which should be a constant, so the reference signal is a constant, but the disturbance is periodic disturbance. The load torque is periodic. Now that's not sinusoidal, but you can decompose a periodic signal into a Fourier series of sinusoidal components, and then look only at the first 10 components. Let's say they are significant from the point of view of power, and then you have like a superposition of a certain number of sinusoidal signals acting on your drill. Yes? And the reference, of course, is constant. So let's say that you have selected 10 different frequencies which are significant harmonics of your load torque, and the reference is a constant, so it's frequency 0. Now, this is something which we have not yet discussed. What happens if you have the disturbance and reference signals are not one frequency? Until now we only discussed one frequency. But what happens if they are actually superpositions of several frequencies? So let me erase this. So we have the standard feedback interconnection P and controller C. Reference, disturbance, okay, and now let's suppose that in the standard feedback interconnection we have R of T is a finite superposition of Rj cosine of omega j T plus phi j. J belongs to some index set, capital J, capital curly J. Okay, so and these frequencies may contain also the frequency 0. So then the corresponding term is constant. Yes? So constants and sinusoidal signals. And suppose that D, the disturbance, is similar. Yeah? So not the same but similar. Then what can we do? Well, based on all the reasonings that we did earlier today, what we need is a controller which does what? Who can tell me the answer? Stabilize the system, correct, and I would like the steady state error to be 0. How can I, what kind of controller can achieve that? Steady state error means that after a very long time it should converge to
so it should have all the
it should have poles, so the controller should have poles at all the relevant frequencies. We need C of I omega j should be infinity, which means poles at all the frequencies omega j, and it will not work if the plant has a 0 at those points. So the plant at the frequencies I omega j should not be 0. Yes? So this is what we need in order to solve the problem. We need first we have to check that the plant is not 0 at those frequencies. And I'm still talking in the seesaw case, but of course we will generalize this to MIMO. Yeah? So the plant should not be 0 at the relevant frequencies, and the controller should have poles at all those frequencies. Why? Because then the gain of the controller will be infinity at all those frequencies, meaning at the points I omega j. The gain of the controller will be infinity, which means that the sensitivity at all those frequencies will be 0. And when I say at all those frequencies, I mean the sensitivity at I omega j. Yes? So the sensitivity will be 0, and if the sensitivity is 0, then it means that the error in steady state will converge to 0 for all those frequencies. Yes? Now, if the signals D and R contain components in addition to this, so if there is some other component plus R0 of T, if there is some additional component which is not sinusoidal, then of course the steady state error will not tend to 0. And for this, to somehow defend also against whatever other noise there might be, we want in principle to make the controller as large as possible also at other frequencies. Yes? So when we choose, so our criterion is not only to have the controller to have poles at the frequencies that we care, but in general we would like it to be also as large as possible also at other frequencies, or at least in the frequency range that is of interest to us, because not every frequency is of interest to us, but there is usually a range of frequencies, an interval of frequencies which is of interest to us, and in that range we would like the controller gain to be as large as possible, like always in control theory. We want the controller gain to be large in the range of interest. But for the tracking and disturbance rejection problem, oh, I didn't tell you that. The name of this problem is tracking and disturbance rejection, because you have tracking a reference and rejecting a disturbance. So the name of this problem, the name of the problem when you say, okay, I have an R and a D of this form and I want the error to tend to 0, the name of this problem is called tracking and disturbance rejection problem. And to be able to solve it in this context, you need, of course, the stability of the closed loop system and these conditions. Yeah? Okay. So this was a quick introduction to the internal model principle for finite dimensional linear systems. Yeah?
What is exactly what you mean by the concept of internal model principle? It applies to which part of the
why is it called internal model? Oh, very good question. Yeah.
I mean, which is the exact concept with respect to all the explanation that you already made? I mean, which is the part that we call internal model principle?
Yeah. So yeah. Okay. Of course I should have explained that. Okay. Let's look. Okay. Let's look at this system. Assuming that there is no such noise, yes, it's purely sinusoidal signals. R and D are superpositions of sinusoidal signals, which may contain constants as well, yes. And let's look at how this works. So I have so far not told you why is it called internal model principle. It's a very important point. So let's look at this system, and let's say that we have waited for 100 years and the system is still working. So after 100 years the transients have gone to zero, and so we are now in what is called the steady state situation. So in steady state the error is how much? Zero. Yes, in this situation with this R and this D and with these conditions the error is zero. Yeah. So look at this system now. How does V look like? How does V look like? V. No, it's not zero. It's not zero. If V would be zero, then the system would work in open loop. No. How is V? So yes, all the signals, Y and U and V, they all are of this type. Superpositions of sinusoids of the relevant frequency. So you have to collect all the frequencies which are present in R and all the frequencies which are present in D. They may be different. Okay, and you collect them all, as that's your collection of frequencies, and you know what? Let's say they are the same, because I can simply put some of the coefficients 0 here and some of the coefficients 0 here. So we have a fixed set of frequencies, omega j. Yeah, so they contain all the frequencies from R and also from D, and we have these conditions. Yeah, now. Under these conditions, we know that every signal in the closed loop system, which means U, Y, V, and E, will be according to the superposition principle. You know that in linear system theory there is something called the superposition principle, which means that if you have two signals applied to the system, then the response of the system is the sum of the response to the individual inputs. Yes, that's everybody knows. Okay, so we know that for each individual sinusoid alone, the response of all the signals would be a sinusoid of the same frequency, and of course multiplied with the gain of the closed loop system at that frequency, which in the case of the tracking error, that gain would be 0. Yes, so in the case of E, that would be 0, but in the other cases, Y, U, and V, it's not 0, it's something. Yes, so there will be a sinusoidal oscillation here and here and here and here and here. Yeah. But on here it would be 0. Here it would be 0 in steady state. Now you take the superposition principle, so you take the sum of all these different sinusoids. So here it will be a superposition, and here and here and here and here and here, and here it will be still 0, right? Okay, so the signal V would be some superposition of the relevant frequencies, and the input of C is 0. So you see this controller receives no input, but it produces a superposition of sinusoidal signals, which is exactly what is needed, exactly at the correct amplitude and phase, because it cleverly reaches that situation, that it produces these sinusoidal signals at the exact correct amplitudes and phases, so that putting everything together and reaching E will be 0. Yes? There is only one clever choice for this signal, which will make E equal to 0, and the controller will produce it. And if the controller by chance deviates, let's say that at some stage, I don't know, a glitch occurs. Let's say that this is running on a processor, and the processor misses one cycle, so that's a glitch, right? Or misses 100 cycles of the processing time, yes? And then the phase and the amplitude of the output will have a glitch, it will move. Then what will happen? A transient will occur, and you have to wait again for a few seconds, and again it will correct itself, and this will become 0, right? So it automatically corrects any glitch. It will come back to the steady state situation in which this will be 0, right? So, but what is important for the name is that the controller receives no input, but it produces a signal which looks exactly like the reference. No, I mean, it's in the same class of signals. It's not equal to the reference, but it is in the same class, meaning superpositions of sinusoidals. So it will produce a signal of the same class as the disturbance or the reference. So that means that the controller on its own is able to produce the same signals as the reference and the disturbance. Yes? The controller, while receiving nothing, zero input, is able to produce permanently the correct signal which will keep the system at 0 error, which means a superposition of the same sinusoids like R and D. So that means that the controller is an internal model. It is a model of these okay, if we imagine that these D and R signals come from some external oscillator. Yes, because we can, mathematically speaking, we can construct an unstable system, which is usually called an exosystem, which is an unstable system and which generates R, and it also generates D. Yes? This is an oscillator. It is a collection of oscillators. And this collection of oscillators generates R and D. Yes? For mathematical considerations, it's very convenient to model the external signals as being generated by such an imaginary external system, which is called the exosystem. And now we realize that in steady state, the controller can also generate the same signals, right? We just said it receives input 0 and it generates the same signals like the exosystem. So that means that the controller is an internal model of the exosystem. The exosystem is an imaginary system somewhere outside. We don't see it. We only receive the signals from it. Yes? And the controller is able to generate the same signals on its own without any input like the exosystem. And for this reason, we call such a controller an internal model based controller, because it has a part, at least a part of it, not all the controller, but it has a part which can generate the same kind of signals like the external signals which come from the exosystem. Yes, so the controller contains a model of the references and disturbances that come from the outside. So the simplest example, if we go back to the beginning of today's lecture, is a PI controller. The PI controller contains an integrator. An integrator, if you give it 0 input, what is the output of it? An integrator with 0 input, how is the output?
Depends on the initial condition.
Yes, so it keeps the initial condition constant. So the output is a constant. If the input is 0, the output is a constant. So an integrator is able to generate constants. And so the integrator part of the PI controller, because there is also a proportional part, but the integrator part is in fact an internal model in the sense that it can generate the same type of signals, constants, like the disturbance and the reference. Yeah? No, this is still going off.
Half an hour is the maximum.
Ah, half an hour, I see.
After
Okay.
that, if it's not correct, connected to the power, press the power for private.
Ah, okay. Okay.
What does it happen when you have an ecosystem and you can't apply the...
Okay, so hopefully we'll get to that tomorrow. So listen to, we have a question here. What about nonlinear systems? So in nonlinear systems, this whole story can be redone for nonlinear systems, but it gets much more complicated because you cannot think in terms of transfer functions. You don't have in nonlinear systems. You don't have transfer functions, and the external signals are not necessarily sinusoidal signal, but they can be any signal generated by an unstable exosystem. So that can be really a lot of things. You have an unstable exosystem. The restriction that usually is imposed that the exosystem generates bounded signals. So you have an unstable exosystem generating bounded signals, and then the controller has to, after a long discussion, which we may hopefully do tomorrow, the controller again will contain an internal model, which means system capable of generating similar signals as the exosystem, such that the error will tend to 0. So the broad ideas remain valid for nonlinear systems, but the reasoning becomes completely different because you cannot think in terms of transfer functions. Okay, now that's it. Now I really finished this informal part for which I had no slides. The internal model principle for finite dimensional linear systems. And now the plan is to give you some background about infinite dimensional systems, and more precisely not about any infinite dimensional system, but about a class of infinite dimensional systems which are called well-posed linear systems. So I will give you background about those, and then I will move into a paper which I wrote together with Richard G. Barber many years ago, which is about the internal model principle for well-posed linear systems. So that is a plan more or less for today, and then tomorrow the plan is to discuss a nonlinear case. So let's see what so now I have to move into giving you background about what is a well-posed linear system. So that's an entirely different topic. We have to take a break of 1 minute, relax, and then start another different discussion. This is where no, that's impossible. You probably can't read the green part, but we will be able to overcome that by me telling you. So I want now to introduce a class of systems which are called well-postlinear systems, which is basically the extension, let's say the natural extension of finite dimensional linear systems, extended to the situation when the state space is a Hilbert space. That is the purpose. Now I don't know, some of you maybe have heard of what is a well-post system. I know Nathaniel, you know what it is, and anyone else knows what it is? You also? Sorry? Sorry? It's close to that, yes.
Actually, you're right, but it's used for many things.
Yeah.
So what's the difference?
Well, I will tell you. It is that, but you have to be precise about in which spaces you work. So, okay. Other than Nathaniel, nobody knows the concept of well-post system. So it's really okay. There is a big book, the red book by Olaf Staffans, called Well-Post Linear Systems. So it's not an easy read, but it is sort of the basic book about that topic. But the way I present it is quite different from and what I am presenting you is based on a survey paper which which I wrote together with, this is a green part that you cannot read, I wrote it together with Mariusz Tucznak, and it was published in Automatica in 2014. Okay, now what is a well-post system? So Borjan already made a guess of what it is, and is more or less right. So it is. Sorry.
What's the difference between this? It's for any input there is a unique output.
Let's put it more precisely. For any initial state and input, there is a unique state trajectory and output function.
You have to regard
So you.
generator.
So you have input and initial state, that is what goes into the system, and what comes out is output function and final state. So a system has an input function and an output function. Input signal, output signal, like in finite dimensional system, yes? So well-posed is it's written in words here what it means. Well-posed means that if you take any finite time interval, yes, from tau to t, and you have an initial state, and I said the states are in a Hilbert space. So you take an initial state in this Hilbert space, and you have an input function defined on this time interval from tau to t. Then what the system responds with is an output function which is also defined, you see, an output function also defined on the same time interval, and you have also a final state, where is it written, x of tau, x of tau is the initial state. Where is the final state? X of t. X of t is the final state at the end of this time interval. So the two quantities x of t and y depend continuously on x of tau and u. Yeah? So there are two data quantities and two response quantities. X of tau and u are the data, and x of t and y are the response of the system. So there are two aspects always, the input and the state, and then the output and the state. Yeah? And there must be a solution, so there is always a solution, a unique solution, and there is continuous dependence. So the final state and the output depend continuously on the initial state and the input. And when I say continuously, then at least in this context, I mean in the L2 norm. So the input function u is measured in the L2 norm of this interval from tau to t, and the output function is also measured in the L2 norm from L to t. Now, u and y are not scalar functions like in the discussion that we had until now. They are with values in Hilbert spaces. For example, if you have a PDE, then the input may be the trace on some part of the boundary, some trace, it means there are many different traces, some trace on some part of the boundary, that may be the input function, and then at any given moment the trace is a function, so it lives in a Hilbert space, and similarly the output may be, for example, another trace on some other part of the boundary, and so that is again at any given moment an element in a Hilbert space.
You just write down the system, so it's itself.
Yes, I will write it down. So,
Just one question. I
yes.
think people, the engineers here are familiar with Hilbert space and norm.
Oh, but I'm sure you already survived the course with Marius about PD, and you survived the course with Enrique a few days ago. So I suppose everybody knows what is a Hilbert space and a norm, right? Everybody? Is there somebody who doesn't know what is a Hilbert space and a norm?
I don't know what it is.
I don't know.
Okay.
So maybe it's something worth mentioning.
Okay. So should I? Wow, but that would take a long time.
Just the definition of the norm.
Okay. Okay. What?
It's the other.
Is the other dust?
Here is.
Ah. Does it matter?
Maybe not.
Okay, everybody knows what is a vector space. So I don't have to say what is a vector space. Okay, that saves us some time. Okay, now in some vector spaces, you have defined something called the inner product. The inner product is a function which maps a pair of vectors into a number. And this number is denoted like this. And this is called the inner product between x and y. And this should have the following, so inner product. And this inner product should have the following properties. X plus y product with z should be equal to x product with z plus y product with z. If I multiply lambda is a complex number, lambda times x product with z should be equal to lambda times the product of x and z. Yeah? So in other words, the product between x and y should be linear in x. Yeah? Now if I swap them over, if I have zx instead of xz, then that's a complex conjugate of xz. Yeah? And that automatically implies that the inner product is not quite linear in the second component. It is what is called anti-linear, which means that it has this sort of property, additivity, with respect to the second component. But if I take lambda x in the second component, then what comes out is not lambda but lambda bar. Yeah, everybody follows what I'm saying? Okay. Then another property that is required of any inner product is that when you multiply a vector with itself, then that must be positive. Always. And if you have anything else, I think that's all. So any function defined on pairs of vectors which satisfies these four properties is called an inner product. So
Unless it is.
Yeah.
yeah, of course. Unless that is 0. Thanks. Okay. Now, the simplest example of an inner product, which you know from elementary school, is that if you have the space X is equal to C to the power n, which means vectors with n components, then the inner product of two vectors, X and Y, should be the sum, so x1 times y1 conjugate plus x2 times y2 conjugate, and so on, up to xn times yn conjugate. Yes, that is the usual kind of inner product that is used in linear algebra, and you can easily see that it has all those properties. And when you have a space with an inner product, then you can define a norm on this space in the following way. The norm of X is equal to the square root of the product of X with itself. So this is a definition, and you can define a norm in this way. And then this norm has certain nice properties, like, for example, X plus Y in norm is less than X norm plus Y norm, which is called the triangle inequality. Yes, you have probably heard of that one. Then if you multiply a vector with a number lambda, with a complex number lambda, and you take the norm of it, then lambda absolute value goes out, and times the norm of X, yeah, lambda absolute value goes out, and the norm of X is always positive unless unless X is 0. And what else? That's it. Sorry?
The inner product in inequality.
This is only a special inner product.
These properties of the norm are true for any norm. So I mean any function with values in positive numbers which satisfies these three properties is called a norm. Have I left something out here? No. Okay. So any function which satisfies these three properties is called a norm. But in particular, if I define a norm in this way, then it is a norm. So I mean it satisfies these properties. Moreover, if I define the norm in this way, then it has some additional nice properties. For example, the product between X and Y in absolute value is less than the norm of X times the norm of Y. This is called the Cauchy-Schwarz inequality, which you may have heard of. I mean, I'm sure most of you have. And this is, of course, specific to this choice of norm. There is another nice identity which is specific to this kind of norm, which is called the parallelogram identity, which is that X plus Y, X plus Y squared plus X minus Y norm squared is equal to twice norm of X squared plus norm of Y squared. This is called the parallelogram identity. It is not true for any norm, but it is true for a norm which is obtained from an inner product. Yes, and actually, it is what characterizes the fact that the norm is derived from an inner product. I mean, if this identity is true, then it means that the norm has been obtained from an inner product. It's if and only if. Yeah? Okay. Okay, so this is a norm. This is a space with inner product and the corresponding norm. That's not yet a Hilbert space. Yeah. Okay. Was it too fast, or is it okay? This speed is okay. 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 Now, can I delete this? I have no choice. Okay. Okay, now we have to discuss what is a Cauchy sequence. So you have a sequence xn in a space in which you have an inner product, and hence you have also a norm. So this is a sequence. I shouldn't write it like this. I said, right, we have a sequence such that each term is in X. Yeah, that's a more correct way to say it. Now, and this is called a sequence in the space X. And this sequence is called convergent. Convergent if there exists an x0 in the same space X such that the norm of xn minus x0 converges to 0. Now, the norm of xn minus x0, that's a number, right? That's a positive number. And what does it mean that a sequence of positive numbers tends to 0? That I don't have to tell you. So if this is the case, then we say that xn converges to x0. If the norm of the difference tends to 0, then we say that xn tends to 0. So this is a convergent sequence if this happens. Now this was a definition of a convergent sequence. Now I tell you another definition which is closely related. So we have again a sequence in this space X, which is a space with inner product, and we say that this sequence, so xn convergent, and now we say xn is a Cauchy sequence. Cauchy sequence if the difference between xn and xm converges to 0. So now I do not compare to some fixed element x0, but I compare between terms of the sequence. And if the difference between the terms in norm tends to 0, then we say that it is a Cauchy sequence. Now, what does it mean exactly to say xn minus xm tends to 0? N and m both tend to infinity, but at any arbitrary rate, right? So in other words, for any epsilon positive, there exists an n which depends on epsilon, and it is a natural number, yes, such that the norm of xn minus xm, yes, this expression is less than epsilon if both n and m are bigger or equal to this n epsilon. Yes, so if both n and m are big enough, then the difference, the distance between them, which is the norm of the difference, we say that the distance between 2 points usually means the norm of the difference between them. Yeah? So if n and m are big enough, then the distance between xn and xm is less than epsilon. Yes, that is the concept of a Cauchy sequence. Now it is very easy, and I leave it as an exercise to prove it, that any convergent sequence is a Cauchy sequence. Yes, this implies this. Any convergent sequence is a Cauchy sequence. Yeah? The other direction is not true. In general, it's not true. So I put an arrow, and now I specify that this other, the opposite direction is in general not true, but if it is true, then the space is called a Hilbert space. Hilbert space. Yes, so this is conditional. The implication from the bottom to the top is only if the space is a Hilbert space, which is not always true. So there are spaces with inner product which are not Hilbert spaces. So, sorry?
That norm is the one you have.
Yeah. I'm talking. Yeah. So X is a space with inner product. Is a space with inner product. This is true also otherwise, but inner product. So in fact, what I did here, that convergent sequences and then Cauchy sequences and these two directions, it's true not only for spaces with inner product, it's true for any normed space, for any normed. So if this is, if instead of X is a space with inner product, I would have said X is a space with a norm, and I defined you what is a norm earlier. If it is a space with a norm, then I define in the same way, I define what is a convergent sequence. In the same way, I define what is a Cauchy sequence. And then I say, this implies this. And if it's true in the opposite direction, then it's called a Banach space. Yeah? So, so that's a more general region in which we have normed space, and then a normed space can be a Banach space or it can not be a Banach space. Yes, but we are only interested in this course about Hilbert spaces, so that's the same story, but the norm is defined by an inner product. Yeah? Okay, so now we know, should I go into examples of inner product spaces that are not Hilbert spaces and are Hilbert spaces? Does anyone need an example of an inner product space that is not a Hilbert space? Who wants an example? Nobody wants. You want. One, not enough. 2, 3, 4, 5. Okay, then we do it. Let's do it on. Consider the space X is equal to L1. Do you know what it means, L1? L1 is a space of all the sequences of complex numbers, sequences of complex numbers, for which the sum of the absolute value of xn is finite. Yeah? That's L1. Who has heard of this space before? Okay. Now, on this space, there is a natural norm. The natural norm, I tell you, but we will not use it. But I tell you what the natural norm is. It is exactly this. This is a one norm of X. This is called the one norm. And with this one norm, this space is a Banach space. I told you earlier. So there is a norm, and any Cauchy sequence is a convergent sequence. Not so easy to prove, but it's true. Any Cauchy sequence is. I do it in my course in functional analysis. Any Cauchy sequence is convergent, and therefore this is a Banach space. Okay, now we decide to use on this space a different norm. And this different norm is derived from an inner product, and the inner product is x inner product with y is equal to the sum of xk, yk bar, which is the most natural way to define an inner product. Yes, k goes over all the natural numbers. Yeah? So it's easy to see that this is an extension to infinity of the inner product that we had earlier, right? Instead of doing sum from 1 to n, we do sum from 1 to infinity. Yes? So this is an inner product. It can be checked easily. And then, of course, it defines a norm. So the corresponding norm is the square root of the inner product of x with itself, which means the square root of the sum of xk absolute value squared. K goes from 1 to infinity. Yeah? Is that clear? Okay. Now, fine. So here it is a space. We have a space with an inner product and the corresponding norm. And now my claim is that this inner product space is not a Hilbert space. And to prove that, we have to find a sequence in this Hilbert space which is not a Cauchy sequence which is not convergent. So let's define it like this. I need more space to do it, so I do it here. So I define x1 is 1, 0, 0, 0, 0, 0, up to infinitely many times. That is one vector in x. Yes? Is that obvious? Yeah? It's a good vector. Now, x2 is 1, 1/2, 0, 0, 0, 0, 0, infinitely many times. The third vector, x3, is 1, 1/2, 1/3, 0, 0, 0, and so on. The fourth vector is 1, 1/2, 1/3, 1/4, 0, 0, 0, 0, 0. Now it's pretty obvious how this continues, right? Okay. Let's check if this is a Cauchy sequence. So how if I
just do a difference between a sequence and the sequence of a sequence. Because it might be really confusing if you see it the first time.
Yes, it is, yes. So you see, this is a sequence of sequences. Yes? So a vector is a sequence because it's
So when you say vector,
sorry?
when you say vector, it's an element of a vector space, not a vector in real world.
When I say vector, it's an element of a vector space. Yes, exactly.
I don't know if
Well, we defined what is a vector space, and now we deal with this specific vector space here. So any element of it is called a vector. Okay? So we have here a sequence of vectors, and each vector itself is of course a sequence, because the space consists of sequences. I should have given a different example with functions. It's too late now. Okay. So let's evaluate xn minus xm. Yeah? Squared. So let's, for simplicity, assume that n is bigger than m, because it doesn't really matter. I mean, it's symmetric. If it's the other way around, then you do. So let's assume, for simplicity, that n is a bigger one. N is bigger than m, and we evaluate this difference. So you tell me, how much is it? So we let's say this minus z. If you take this minus z, what remains? Only this term and this term, right? If I take x4 minus x2, then this disappears, and what is left is only 1/3 and 1/4. So in general, only the terms from n minus m plus 1 up to n remain, right? So the norm is how much? Is 1 over n minus m plus 1 squared, right? Plus 1 over n minus m plus 2 squared, and so on, up to 1 over n squared, right? Right? So this is a difference between two terms. It is all the difference terms squared added together. The difference norm squared, right? Okay. Good. And now this is less than, actually strictly less than, the sum of 1 over k squared, where k goes from n minus m plus 1 to infinity. Yes? So if because this stops at 1 over n squared, but I could add up to infinity if I wanted, and then it is less than that. Okay. Now what happens if n and m are both big? What happens if they are both big? Does this tend to 0? It does, because this is a tail of a convergent sequence. Sorry, a convergent series. This is a remainder, okay, of a convergent series. This is a sum of 1 over k squared from 1 to infinity is finite. Right? You know that it's actually pi squared over 6, but it's a finite sum. So therefore, if I take the tail of it, it means I take the sum only from a certain point up to infinity. Then the further I take this tail, the smaller it gets. It actually must tend to 0, because that's actually the definition of a convergent series, right? That the tail tends to 0. Yes. So this tends to 0. So yes, it is a Cauchy sequence, right? It is a Cauchy. This is a Cauchy sequence. Cauchy sequence. Cauchy sequence.
I think there is something wrong. You have to start with 1 over m plus 1 square or something like that.
Here?
Yeah.
Well, let's try it with 4 and 2. So if I take x4 minus x2, what remains is
Okay, this
1/3
is
and
a
1/4.
special case because it's the same.
Sorry?
4 minus 2 is 2. In this special case, it's true because it's the same. If you, I say you have to start with m, not with n minus m. But if you choose 4 and 2, it's the same.
Wait, let me check.
You end up.
You are right. It's m plus 1, not n minus. You're absolutely right. M plus 1.
Yes.
M plus 1. M plus 1.
Otherwise, this sequence, you have to change it on the theory.
You are right. Please correct if you took notes. It starts with m plus 1. M plus 1. Okay, and then here m plus 2 and so on. M plus 2. Okay, thank you.
It's because the series doesn't converge to 0 on the right hand side.
What?
This series, you have to change the starting point. Otherwise, this wouldn't work.
Yeah. M plus 1. Yeah, that's it. Yeah, of course it wouldn't work. If it would be like I wrote, it wouldn't work. Yes. Okay. Okay, so it is a Cauchy sequence. Now, let's see if it is convergent. So, if it's easy to show that if a sequence of sequences converges in the sense that we defined earlier, then the first component of it converges to the first component of the limit, and the second component of it converges to the second component of the limit, and so on. That's very easy to show. I mean, extracting a certain component of a sequence is a continuous operation, so that if I extract the first component, it must converge to the first component of the limit. The second component must converge to the second component of the limit, the third to the third, and so on. So let's see what would be the limit if it is convergent. So the limit of the first component would be how much? 1. The limit of the second component would be 1/2. The limit of the third component would be 1/3, and so on, 1/4, and so on. So if this sequence would have a limit, then the limit sequence would have to be x0 equals to 1, 1/2, 1/3, 1/4, and so on. Yes, that would be the limit sequence. But this limit sequence is not in L1, right? It's not in L1. Because the sum of 1 over k is infinity. Yes. So therefore, the assumption that there is a limit sequence was wrong. It has no limit sequence, and so therefore this is a Cauchy sequence in which has no limit. Okay. Now there is. So there are inner product spaces which are not Hilbert spaces. For example, this one. But if that happens, if you have an inner product space which is not a Hilbert space, then you can always enlarge the space, and this enlargement is called the completion of the space. And this enlargement, actually we need that concept later today. So you have a norm with which a space is not complete. If that happens, then you can always define a unique larger space which is complete, such that our initial space is a subspace of this larger space, and moreover every element in this larger space, which is a completion, can be written as the limit of Cauchy sequence in the original space. So I repeat that. You have an inner product space which is not a Hilbert space. Then you can define in a unique way a Hilbert space which is called the completion of your original inner product space, and which has the following properties. So the completion has the following properties. It is a Hilbert space. It contains your original space as a subspace with the same norm. And every element in the completion is the limit of a Cauchy sequence in your original space. Yes? So in the case of this space, this is a Cauchy sequence which, as we have seen, has no limit. But in the completion, it does have a limit. In the completion, every Cauchy sequence has a limit. So in the completion, this is the limit, 1 over k. And in the completion, the completion has the same norm. So I mean, the norm of the completion is an extension of the original norm by continuity. So the norm on the completion is defined by the same formula. So the norm of this limit is simply the sum of 1 over k squared from 1 to infinity. That's a norm of the limit in the completion space. And this completion space is in fact a space called L2. So in general, if we have a vector space which is an inner product space and it is not a Hilbert space, then I denote the completion with a tilde. So this is a completion of V, completion of V. Yeah? So in our specific case, the completion of this X, can you see that? No. The completion of X would be a space called L2, which consists of all the sequences xn of complex numbers such that the sum of xn absolute value squared is finite. And on this norm, on this completion, the inner product is defined by exactly the same formula, because, as I said, the inner product on the completion is an extension of the original inner product. So it's the same expression, and therefore this expression here is exactly. This expression is the norm squared of X. Right? Sorry?
Another example illustrates something which people don't notice, but actually one thing people are aware of is that this is how we construct the real numbers.
No. You have originally the rational numbers, yes, but they are not a vector space. It's not a vector space. So it's related, of course. It is what you say is a concept of a completion of a metric space, a completion of a non-complete metric space, which is, of course, the same. But what I defined is a completion of a vector space. So in that sense, what you say is not, it doesn't fit exactly, but it is very closely.
Q is a vector space over Q.
Yes, it is a vector space over Q, and then you have to deal with a theory of vector spaces over Q, and you might be able to squeeze it in. Yeah. Okay. Now. So this is the concept of a completion of a vector space. Yeah. So you may have originally an incomplete vector space, meaning with an inner product but not complete, and then you have to add to it all the limit points, all the possible limit points of Cauchy sequences. You have to make all the Cauchy sequences convergent. So you have to add artificially all the possible limit points of Cauchy sequences, then you get a larger space, and this larger space is called the completion of your original